Okay, thank you. So I think Stefan set up the stage very well for me. So this is probably the first time in the last 10 years or so that I don't have to say what a superconducting qubit is. And speaking of first times, if you couldn't tell from my name, you now probably can tell from my accent that this is not the first time I've been in Spain. But curiously, this is the first talk I ever gave in Spain, even after been working in experimental physics for 15 years or so. So I'm very excited about it. So thanks for the opportunity. Right. So this is gonna tie in a lot of the things that have been discussed over the last 2 days, in terms of what can you do with a quantum computer in terms of machine learning that is challenging or is supposed to be challenging for classical machines. I'm going to have two parts in the talk. One part is kind of what can machine learning do for quantum, and the other part is going to be what quantum can do for machine learning. So in the first part, I will talk a little bit about some of the stuff that Stefan was showing for readout, determining the readout output of a superconducting qubit, and how to classify those and how to reduce error as much as possible. And in the second part is actually I'm going to center on this, which is I'm going to do supervised learning on a quantum processor on some particular data set. Right. So this is a subset of our idea factory. So Iswar was mostly concerned with what I'm going to be talking in the first part. Wojciech was an intern at IBM last summer, and then he was working mainly towards the classifying problem, the quantum classification. And then Kristen and Jay have been also key components on this work. And I just limit myself to push the buttons they tell me to push as well as I can. OK, so I'm going to start by defining the problem. And sorry for the math-dense slide. But we want to define what does it mean to do supervised learning. So we have a data set that consists of vectors and labels. And we are not given the labels, but we are given another set, which we call the training set. And that contains both vectors and labels. And the idea is that we can try to find a function between the data set and the labels for the training data set in a way that when we extrapolate that function to the test data set, it gives us a good ratio of success. And this is a bit general, but I'm going to be particularizing to support vector machines because they're very nice in some way, but also because our quantum approach has some relation with that at some level. And the idea of the support vector machines is that you can have the data that you want to separate or you want to train, and you can focus on a very few points on that data, which is what are called the support vectors. And that gets rid of a lot of dependence on outliers they might have in the data and so on. So it's very nice in that sense. So I'm going to have a single slide on support vector machines. And I will go through this in some detail because it's going to be important to make some arguments later for complexity and so on. So what normally one does when it applies support vector machines is you have a set of data that let's suppose is separable. But it's given to you in a way that is not separable. So for example, here, the simple example where you have a one-dimensional data, and you try to separate these two sets, and you kind of cut the line in a single way that separates it. But if you go to higher dimensions, and then you map your data to the data itself, and then the square of the data, you have a parabola here, and then now you can separate it cleanly. So the task of support vector machines is to maximize what is called the street, the distance between the support vectors. And you do that doing a constraint optimization problem, where you say, I want to minimize the norm of this vector, which is the same as maximizing this width here, under the constraint that all the green data, say, are in this side, all the yellow data are in that side. So you can go to you can write this in a Lagrangian form for the constraints, and then your problem is reduced to say, I want to maximize with respect to these alphas and minimize with respect to the W and B. So it's like finding a saddle point. And because you want to maximize with respect to the alphas, the only alphas that are not going to be 0 is the ones for which this inside the bracket is 0. And this is precisely the support vectors. So only the support vectors give you information about what cutting you need. And you can take this to the what is called the dual form, where you actually can express your minimization problem or optimization problem in terms of inner products of your vectors that compose your data. And this is very important because you don't need to look at the data. You just need to look at the inner product of the data. So you can apply kernels. You can apply nonlinear functions to the data. Like this is a very simple one, but you can go arbitrarily complex. And as long as you can efficiently estimate the inner products of those kernels, you're going to have an easy time relatively solving your problem. So when we say, can we do something with quantum systems that is difficult with classical systems, we have to bear in mind that there might be data sets that are complex, or they look complex, but when you try to estimate the inner product, you actually realize that it's not that complex. So we want to think if there are data sets where actually the inner products are complex. So that sets the stage for support vector machines. But now I'm going to change gears a little. I'm going to talk about machine learning for classifying trajectories in readouts. I'm going to go relatively fast through here. This is actually a part of the talk I put in here because I had a few slides on superconducting qubits, but because Stefan talked about that, I fit it with some older data. So this is from this paper 3 years ago. And, and the idea is that you have a lot of single-shot signals that are coming to your computer from the experiment, and you want to determine whether those are zeros or ones for the qubits, and this is the typical noisy single-shot signals. If you take thousands and thousands of those and average them, they look much nicer, and you can see a clear separation. But now when you are in the real experiment, and you are doing an algorithm, you want to know every single shot, whether it's a 0 or 1, to use feedback or to use feedforward or whatever. So you need to classify this reasonably well. So we define an assignment fidelity this way. So it's 1 minus the probability of measuring 0 when you prepare 1, and the probability of measuring 1 when you prepare 0. And then we take those trajectories, we take a number of them, and we discretize them in time, and we treat those discretizations as vectors on which we do the learning. And then we are going to use, for these support vector machines, but we're also going to use the typical method is using discriminant analysis. So you can use linear discriminant or quadratic discriminants. So this is a list of what you get if you use the different methods. So linear discriminant analysis with diagonal covariance, that means that you have a covariance matrix that is diagonal. So there is no a strong correlation between different dimensions of the vector. So you get 95% assignment fidelity. We have 50,000, around 50,000 trajectories, and we use half of them for training, and then we test that training on the other half. And then we discretize the time in this way. And if we go from diagonal linear to just linear, where we allow the covariance matrix to be non-diagonal, we get improvement. Then we get better improvement if we go to quadratic dimensional analysis, discrimination analysis, which is telling us something. It's telling us that there is non-linear effects in our problems because we get a better answer here. And when we go to support vector machines, we get better. And when we go to nonlinear support vector machines, which is applying a nonlinear kernel, we get even better here. So this is telling us there are some nonlinear effects that are affecting our readout fidelity. And our hypothesis is that this is T1 events that are affecting the readout. So with that hypothesis, we use K-cluster analysis to find, this is unsupervised training, and we try to find classes data that we can classify as different events. And there is one clear one that, as you see here in the green, that starts in the 1 state, and then at some point it goes to the 0 state. And we can identify that as a T1 process. And we get about 10% of those, which is consistent with the 30 microseconds for T1 that we observe in our system. And if we remove those events, or we correct for them, then we get above 99%. So these tools are useful for improving the readout that we get in our systems normally. So now I'm going to go into the main part of the talk. So this is, as I was saying, how can use a quantum computer or a quantum processor to do some classification in real data sets. So this ties in a bit of what Seth was saying this morning. Like, are there any data sets that can benefit from quantum? And of course, there is these kind of works, like they're very seminal in the field, and they require the quantum RAM. And we wanted to ask ourselves, without any additional resources, can we do something that is actually advantageous? So our work is very similar to what was recently reported here, but there are some subtle differences with this work. Here I just put this because there's some nice review of some current state of the art. The algorithm I'm going to be describing is the usual that Stefan described also for the chemistry and so on. So we do prepare our quantum system in some state. We apply some gates, ideally some shallow circuit. Then we measure. Then we feed that to a classical machine. We do some optimization, and then we feed back the result to the quantum processor until we find some minimum, and then we look at the answer. So normally, what you do if you take a regular data set, and I take these ones that you can find in the sklearn package in Python, and then you just map the components into the qubits in a separable way. My prediction is that you are not going to do any better than SVMs, and SVMs are typically pretty good at doing this kind of classification. However, if you have this is the way you will do it. You will just apply a Hadamard and then just apply a Z rotation with the angle that is related to your coordinates, and then you'll just go and try to classify on that. What I'm going to be showing is data of this kind, which looks just crazy and random, because it's crazy and random. So they're coming from these kind of patterns. And to answer the question, are they data sets that are hard classically but not hard quantum? The answer is yes, and if only because I'm going to fabricate them. So these data sets are coming from this kind of unitary, where I take Z operators, Z Pauli operators, and I multiply them together for a number of qubits. And I'm going to restrict myself to 2 because otherwise the circuit wouldn't be shallow anymore. And then with this unitary, I apply that to a plus state. And after I have that, I do a random rotation on the canonical basis with a random direction, random angle. And then I project, and then I calculate the parity or the majority of the qubit system, depending on the number of qubits. And then I plot if parity is positive, or if majority is 0 or whatever, is one label, and the other case is 2 labels. This is only for 2 labels. And then you get patterns like this for different random bases. Now, the way we map this is, ideally, you will do a ZZ. So you will do first the single Z goes in a single qubit, the same way I was showing for the Python data sets. But then for the ZZ, because in our architecture we don't have ZZ gates available, we have Z nodes. However, we can parameterize a ZZ this way with 2 Z nodes sandwiching a Z rotation that is related to the product of the 2 features. And this is for a 2 qubit case. So now once you have this mapped, and you can measure the parity and apply the labels. And this is the case that you will get for 3 qubits. And as I said, I'm limiting myself to 2 Cs as most. So now for 3 qubits, you will get this kind of pattern, and this will be the mapping circuit. Now after that, what we do is we apply a short depth circuit, which is the W is kind of equivalent to the W of the supervector machines, because this is going to encode the solution of the training. The solution of the training is going to be a circuit that when I apply it to my input data, it's going to tell me whether it's one label or another. And you do that by using a combination of single qubits and entangling gates. And then you do that for some depth. Right? And finally, we measure in the canonical basis, and this is one example of the whole circuit for one of these points for depth 1. And then in a 2 qubit, we'll measure something like this, and we estimate the parity of this. So the probability of the point being A is 0.33, and the probability of being B is 0.66. So we will label this as B. Now, after we have done that, we have to fit this back into our classical machine, and we need to have a cost function. And the most natural cost function we could think of is actually the definition of the probability of getting it wrong. And that for 2 qubits, for 2 labels, for 2 qubits, has a kind of analytical solution that you can describe this way. For more labels, is more complicated. But if you plot the cost function as a number of shots, it gets stretched progressively because you have more shot noise in your experiment. So this is what we use for a cost function. And then, as Stefan mentioned before, we use simultaneous perturbation stochastic approximation, which is one of the possible optimizers you can use. And what we find nice about this is that you only do 2 measurements, because this can get to a large number of parameters when you have significant depth. So with 2 measurements, you can tackle many parameters. Again, as Stefan said, it's not clear that this is the best we could be doing, and sometimes we get into trouble in some of the optimizations we are doing. It could be due to precisely this choice of optimizer. So it's an open question what we could use instead of this. But as I said, it makes our life easier in terms of parameters. So at every step, we estimate the gradient, and that gradient determines the next value of the angles that we use for our W optimizing circuit and so on. All right, so this was run in one of our 5-qubit quantum experience devices. This triggers the question again of stability, as was asked a minute ago. I used qubit 0 and qubit 1 for these experiments, and you might wonder why, given that during these experiments, the calibrations for qubit 1 gave 15 microseconds for coherence time, which is far away of the best it has been measuring this same qubit, which was like 60 or 70 microseconds, let's say a couple of months ago. So this comes and goes. I have my own ideas of the reasons for this. Other people have other ideas for why this happens. We never agree. But we are too busy, building solutions for quantum to actually explore the science of this. So at some point, we'll get to the bottom of this, and we'll make systems more stable. But yeah, I use qubit 0 and qubit 1 for this experiment. The 2 qubit gate is not too bad. It's just above 95%. And the readout errors are also good. So these 2 qubits were more stable than any other of the qubits that I could see during that time. Even though this was lower, sometimes these qubits will move quite a bit on readout fidelity and so on, so I chose these 2. Now, all that I've said about this feature map comes with an asterisk, because I said that, well, I didn't say, I'm saying it now, that these kind of circuits are sharply hard if you don't have noise. But if you have noise in your system, as we do, then you can simulate classically the quantum output up to some epsilon that depends on the noise. But we can come up very easily with something that is even harder by removing the constraint that this is diagonal. So this is a diagonal. So if we say this doesn't need to be diagonal, so if we add some excess here, for example, then that is classically hard. you're never going to be able to sample that. So we do that by repeating the feature map twice. So we write down the previous feature map. Now I'm coming to one that looks very similar, but it just encoding it twice. And now you see 3 colors here rather than 2, and that's because sometimes we put a gap in between the data to make our life easier. So all I'm doing in this talk is tailoring my problem so that I can actually solve it. So in this case, there is 2 labels, and then there is zeros in between, which belong to neither label. So all my data points are going to come from either black or clear yellow. So now this is the data. And this is as fresh as it gets, because some of this data I was measuring this morning, and actually I started measuring JFK when I was coming here. And if my talk was on Friday, I will have more data than this. But if anyone was on my March meeting talk 2 weeks ago, I showed some data that was very different. It was much worse. But the processor has started to behave a bit better, and now I have data that I'm less ashamed of showing. But this is a gap of 0.3, so it's significant but not too large. So that's how much the 2 labels are separated. And this is an example for dev4 and dev0 of the cost function versus trial steps. So you see that at the end, the dev4 relaxes to a cost of just below 0.1, whereas the dev0 flattens out earlier, and then it stays at 0.2. And if you go to the cost of these 2, you see that the probability of getting the correct label, sorry, going the other way. Right. The probability of getting the correct label is a bit over 0.6 here and over 0.5 for the dev0. And if you see the results, and this is just one data set for dev, I need to get more statistics. But dev0 is significantly worse than any of the other devs. And from doing some noiseless simulations on this, I can almost tell you that if I run these experiments 1,000 times, both from dev, all the devs that are larger than 0 basically will be very similar and very close to 100%. So this is the one data set at dev4. This is the classifying stage where I take the test data and I apply the circuit that I got from the training, and then I see this is the probability of getting label A. So for class A, I get everything above 0.5. So I classify everything 100%, and for class B, I get everything below 0.5. So I can classify everything perfectly as well in this example. So this is a bit more lenient towards your errors, because if you think of a problem like chemistry or some other problem where you need to find the precise value of an observable, that's harder, because you have your error bars, and you need to typical chemical accuracy and all those arguments. Here, all I need to go to reach is something above a threshold, and if my data is good enough, then or is easy enough, then I will have a good chance of classifying even with noise. Now, if the data is closer and closer, it will be more difficult. That will be the case as well for classical methods. I'm not saying this is going to be it's not going to do the classification better than classical or anything, but it scales better. It scales as quantum machines scales, and we know that doesn't scale efficiently for classical methods. So I don't have data on 3 qubits. However, I have simulations. And if you look at the simulations, and this is 10 data sets per dev, you see that it's kind of scary that you need to go to get some reasonable training success. You need to go to some significant depth, even for 3 qubits. So now if I'm going to argue that I'm going to take a data set that has 100 qubits and then 2 to the 100 kind of kernel to do the inner products, then this dev we probably wouldn't be able to label as a shallow circuit anymore. So we believe there are better ways of constructing this for a larger number of qubits, and we are working on that, and we hopefully will have a write-up so you can see more details there. But for now, for the number of qubits we are doing, this kind of method we can try to do the experiment this way. So I think that concludes what I want to say. So thanks.
Thanks for the talk. I have one question. So regarding the future 50-qubit chip of IBM, once it works well and so on, which are your prospects? Do you think with current fidelities you could have some quantum advantage in kind of supervised learning algorithms, or how much should the fidelities improve for that?
You mean to apply this to like doing quantum advantage with like
to having some kind of gain with respect to classical. So, perhaps.
I mean, this is the question that is agnostic to the problem I was speaking. Like, you are asking how many qubits and what fidelities you need.
For machine learning, that's as we were seeing this conference is a hard question, but in general, or for simulations or for.
Yeah, my feeling is that it's going to be similar to. For many problems, like this actually is I label as supervised training, but this is actually it's actually a sampling of circuits, and it's a general problem that quantum computers are supposed to be good at. So how much we have to improve to be able to do that in a way that classical computers cannot do is the answer is a lot, and I can't tell you how much. You can look up the numbers quoted by Google, and they have a pretty good idea of where they're going. We are not too concerned about hitting those numbers, but we are concerned about improving where we are now, because it's a long road, and it's hard to put your sight on a particular metric. Like I would rather see that we double our quantum volume every year, and pretty soon we'll be somewhere, and also it will clarify what we actually need, right? Because also at the same time we are improving our systems to reach quantum advantage. There is also research on classical methods that they keep improving as well. So it's gonna be harder to beat them, right? We had at IBM the recent paper on simulating 50 qubits and so on, right? So
any other question?
Sorry.
I've got a question regarding the optimization method. So SPSA, I don't know much about it. Is it? It's not gradient based, but it's.
It is gradient based. Yeah. So you have n parameters in your problem. So you set a random. You start with a random guess, let's say, it doesn't need to be random, but you have a value for each of those parameters, and you do a measurement, and you get a value for the cost function, and then you move to another value of the parameter. You do another measurement, and then you have a gradient.
I'm sorry, actually, I wanted to say it's not analytical gradient based, so you don't.
No.
And now in the FAHI paper, and actually we together with Microsoft, we also have soon, or very soon, hopefully, a paper where you use a circuit to actually get estimates of an analytical gradient. Do you think that will be better? Have you looked into that? Or?
I haven't looked into that. Whether I think it will be better. I'm personally quite frustrated with SPSA. So
speak about that.
Yeah. So,
So I wanted to ask a question about the efficiency and scalability of these sorts of approaches. One of the challenges that you often run into is saddle points for any kind of optimization problem. And with quantum, you have to pay, order 1/epsilon or 1/epsilon squared cost in order to be able to get the gradients within a fixed error margin. Do you see that for any practical problem, the ability to have a richer family of activations for the system, compensating for the extra costs?
I wouldn't say yes to that. My feeling is that most problems that you have in classical methods, they're going to be there in quantum methods as well.
But these costs aren't there in classical methods. You pay polylogarithmic cost classical. Once we need polylogarithms.
Oh, you mean like the error coming from the error in the experiments? For some, yeah. So for some errors, yeah, there's going to be a problem. And when that starts being a problem depends on the complexity of the problem. That's what I think.
No.
All right, because nobody else is asking one. One thing I've always been kind of curious about is with hardware-specific ansatz is learning against systematic errors that are in the devices. Have you seen instances of learning crosstalk and various other things that are in the system appearing in the model?
I mean, we have looked at crosstalk in particular in our system in a more systematic way, not in a kind of, we haven't yet in a kind of machine learning way of looking at it. But yeah, these are questions that in our QCV program we are considering. And at some point it's going to be important to apply methods. I agree. We haven't yet.
Okay, let's thank the speaker again.